start a new block. And so why, if the maths idea is so important, you can't survive this course without knowing what's in that right-hand column. Okay, the use of undo and the indices, you can't survive this course without it. Okay, you must come to terms with use of these particular parts here. Okay, because it's going to be in your face a lot. Alright, the next thing is the calculus idea. What is with the calculus idea? Now I use an informal approach with the calculus idea. So if I do y equals e to the x again, okay, and I just go and do y equals e to the x, there it is, beautiful, e to the x. Now I'm going to be very informal and very counterintuitive, or very intuitive but counter-scientific. And before I do that, what was e? E was 2.7 something, wasn't it? 2.71 something or other. Let's have a look. Yeah, 2.71828. And did you notice something about that? It doesn't. Let's have another look at that. It doesn't repeat. What kind of number is this? There's no pattern there. Who can tell me what kind of number that is?
Irrational number?
Yeah, because there's no pattern. There's no pattern after the decimal. What a strange occurrence. All right, 2.7. So let's do y equals e to the 2. Let's do y equals... oh, sorry, I've got that completely wrong. Why do I do that? You'll learn that about me. I have my moments. Seniors moments, I call them. All right, y equals 3 to the x. So that's 2 and 3, isn't it? So we'll do that. Now, we know they're going to be similar. The 2 to x will be a bit flatter, so I'll exaggerate it. Okay, still be 1. This one here will be a bit steeper, so I'll exaggerate it. Okay. Now I'm going to do the informal thing. I'm going to plot the M curve. You guys have done this a lot, and you'll do it again. Okay, the M curve. Okay, so the way I'm going to do it, I'm going to cheat. Now this is why we did linears last week. It comes up here again, and I'm just going to use little linears. At that point there, at that point there, gradient, gradient, assuming that it goes up constantly. So the gradients follow. Same here, I'm going to do the gradient, gradient, and then I'm going to plot that. Okay, so down here I've got, well, looks like a very low gradient to me. Okay, so I'll put that point there. This one here. So I'm being deliberately unscientific. You know, you used to have the graph paper at school, didn't you? But sometimes graph paper doesn't teach you the concept. Okay, so this one here. So what I find is that when I go and do this one, yes, it goes through 1 at the same point, but it's just a little bit different. Okay, the two graphs, they're just a little bit different. Let's try this one. It's a bit steeper, isn't it? So it's a bit of a higher value for the M curve. It's a bit of a higher value. So it kind of goes a bit steeper. So if I do that one, it's still got 1 there. But again, it's not quite the same. It looks pretty close, but it's not the same. And we can do tables and tables of this stuff. And we can generate 2.1 to the x, 3.1 to the x, 2.6 to the x, and so on and so forth. And we can continually do that. Now, Leonhard Euler was a great mathematician from, what, 400 years ago, one of the most profound individuals. His name's spelt ruler with an E, Euler, but it's Euler, its pronunciation is Euler. What he did, he said, I wonder if we could do, is there a number where when we did the M curve, you know that's M, you know the differential is M, you know that should be X, you idiot. I did it again. You got to call me out when I make those little mistakes. Okay, you got to say, oi Jason. Okay, and so on and so forth. There's lots of different versions of that. Oh, we could have f of x dash, couldn't we? They all mean the same thing, by the way, the gradient. Is there a number that when we did the derivative, we got that result? Now, without computers and without, because they're so close, it's a reasonable thing, isn't it? It's a good question to ask. Equals this one. Is it true? Is there a number? So that's what he did. He explored that. And guess what he found? This guy. So what he did, he went and did the linears without computers, without space rockets, without all of those things, right? And he went and plotted m dash, okay, y dash equals, and guess what he found? It was exactly, dun, 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 the same curve. Look at that. Exactly the same curve. Wow. So this is lost on too many of our school students coming into this subject. Okay? This means that e to the x has two brilliant properties. One, we can use it to solve algebraic style maths problems, and another one, that it's the easiest one to differentiate. There's no other function that has this property. This is the one, baby. This one has, you differentiate it, and it's the same. So it's unique. It's unique in that way. So that's why we love it. So what's the differential of y equals e to the x, people?
E to the x.
You are a genius. Okay? What is the integral of e to the x?
E to the x.
You are a genius. You are a genius. Okay? You can't, if these crop up in your computations, you do it in your head. How good is this? Okay? This is so, so cool. So where does the confusion come from then? Well, I think it's this culprit. I think knowing that the mathematics has the inverse relationship with learn, I think students think somehow that it should be part of this, and it's clearly not. Okay, so what we'll quickly do is just have a look at the intuitive look at ln of x. So y equals the ln of x. Okay, now the ln of x, what's that look like? Well, this is this actually, what are you doing? I nearly did it. You gave it away. Okay, so the ln of x, who can tell me what the graph of ln of x looks like? Here it is here. Alright, so it goes through 1 and it goes up like this. And it's asymptotic. If you know what that means, it means it never quite touches the y-axis. There's always a little gap there. Okay, alright, so let's do the m curve for the ln of x. Or let's do y dash. So what we'll do is we'll make it as close as we can, and we'll start doing our little linears. This is a cheater's way to do it, isn't it? I love that phrase, cheater. There you go. So we start off with a very steep positive. What's that one? There's your y equals x. Well, it's actually got to be this arm when I'm looking at it that way. So a steep one is that one. So it's a very high value of m. This is what we learnt last week, people. Okay, what's differential calculus all about? You should be at home doing this. That's all it's about, nothing else. Okay, differential calculus. So we've got a very high value, and then we got, for the next one, a lesser positive value, and for the next one, a lesser. They're all positive though, aren't they? And all that's happening is it's getting less and less and less. So if you're really stuck, and it turns out if we go that side, but this is 1 over x. Okay, so that's got nothing to do with e. Over here, they're cousins, very tight siblings. In calculus, nothing to do with one another. Okay, so if we can get that clear and separate that clearly in our minds, this is not such a big deal. Okay, all right. So let's do an example now of some growth work on use of e and ln. Okay, so the big thing that you need for, I'll just do 10 minutes on this, is the idea that you've got an equation, which is what you all learned at school, and what we need in this subject, which is an expression. Okay. Okay, so if I get this guy here and I get asked to find the differentiation, typical textbook question from year 11, then you would write y dash is equal to what? What's
E to the
the
x.
Genius. Okay, so if we have y equals e to the 3x, how are we going to do that one? So this is going to be the chain rule. So the chain rule is my pet gripe about school. Not enough students come out of school loving the chain rule. So let's do it. So let u equal 3x. That's the thing up the top there. And yes, we can do a rewrite. So we do a rewrite. We've got two equations. Now what we're after down here is we're after, and I'm using Leibniz notation for the chain rule, as I always do, we're after dy dx. Now watch this carefully, please, because some of you will never have seen this. We're still going to have dy dx. It's just that we're going to go through something else to get it. And what is the something else that we're going to go through? Now in this occasion, we go back to our equations up here, and we can say dy dx, oh no, it's not dx, it's du. Dy du, now this is the easy one. The differential of e to the u is?
Just E to the u.
Genius. See, we changed the pronumeral, and that's going to happen a lot in this subject. You're going to get stuff thrown at you that's not familiar, but it is, it's just that there's been a change of pronumeral. That's a good example. What about du dx? Here we go. What's du dx? Who can tell me du dx?
Three.
It is 3. So if I've got u equals 3x, then the rule would become u dash du dx would become the exponent comes out the front times 3 minus 1. So we get 1 times 3 is 3. 1 minus 1 is 0. So we get 3 times 1, we get 3. So that's the way you do it. And you're thinking all these people around you who can do this subject, that's what they're doing. Now it's your turn. Okay? So what we've got here is our dy du and du dx. There it is. You're going to have to become masters of this. So dy du is in fact e to the u, and du dx is in fact 3. And so we can rewrite that as 3e to the u. Going further, we can put the u away now, and the u was 3x. Now I know some of you will have learnt shortcuts. Please don't do it to yourselves. There will be questions that crop up where the shortcut will betray you. Use Leibniz notation, build your chain up, get used to it. In Maths 1 and Maths 2, you're going to use the chain rule a lot. And if you recall, for those of you that do integration, you will do it in integration as well. Alright, so that was pretty straightforward. I wonder what this expression stuff is all about. What would you recognise if I do that? What does that mean? Well, this is exactly the same thing. It says differentiate y equals e to the x. Hang on a minute, there's no y. Yes, I know that. You're meant to recognise that you have to do e to the x, differential. So if I do e to the x, the equal sign comes out here. What's the differential of e to the x? Dun, dun, dun. E to the x.
E to the x.
Done. Okay, very, very good. This is where it gets a bit trickier. Differentiate e to the 3x. So what we've got to do now is not use the equation crutches that school gave us. We have to really think on our feet. And so Maths 1 will be much more enjoyable if you can manage this. Okay, so what we want to do is the same thing. Let u equal 3x. Leibniz notation will mean we will write du dx. So I've done that straight away. Won't solve that just yet because I want to know what to do. When I had the equation, I could rewrite. So this is going to be a little bit of a test for us because we're going to have d dx. We're still going to have d dx. We're just going to go through something else. I wonder what we're going to go through. And you probably guessed it. We're going to go through du. So the one that we're actually going to write is d du. So I'm going to take this u equals 3x. This d dx e to the 3x, and I'm going to change it to differentiate e to the u. Okay, so that's now e to the u. So that's a big thing that students come in with. Now they do it in 4 unit because they do implicit differentiation. But this expression differentiation is something that you need to come to terms with. It's right throughout the subject, and you'll recognise it now when you see it. Okay. Alright, so this has got an equal sign. What's the d du of e to the u? Dun, dun, dun. Thank you very much. d du of d dx. 3, we did the working up over here. So the beauty of it is that you get the same thing. Now you won't get this hand holding in the lectures. I'm telling you now, the lectures are going to go like that. Okay? And you're going to wonder. So that's why I'm doing this stuff. And I've done this now for 6 or 7 years, helping students just like you, filling in all the blanks and showing you how it works. Alright, so the chain rule, it's very, very important that we do. So let's just do a harder one. But no, what am I doing? Do I want to do a harder one just yet? Maybe if I did one like, what would that look like? I'm sure I'm going to get myself in trouble doing this. Alright, so let's go. Let u equal 3x squared. Well, that looks good. So y is equal to e to the u. That's good. I can do Leibniz notation. Now, what's the problem here? I'm going to change this. I'm sorry to do that to you. I'm going to change it. I'm going to change it because I want it to be something else. I'm going to call it so we can do that. Now it's not sine squared x, it's sine squared x squared, so it's actually not, it's not that, because you know, don't you, that is sine x times sine x. Do you know that?
Yep.
And that is not sine x squared, which is just sine x squared. Okay? Alright, so if I want to put Leibniz notation for this, the problem I've got is that this in itself is a chain rule. Dun, dun, dun. So in order to get this out, I have to simplify this because of the chain rule. So I'm not going to use u. Now, convention is you use whatever you want. I use m and n. M and n are usually enough to get me out of trouble, particularly when we're integrating, because you use u a lot in that. So I'm going to let m equal x squared, and that will allow me to write u is equal to sine of m. Okay, so that's good. So now I can do du dm, and I can do dm dx. So it's looking a bit gnarly, isn't it? So we've got dy dx. We're still going to have dy dx. It's just that we're going to go through a couple of different versions. So we do the y to u. That's that one. So that's e to the u. That's easy. Now du the m. They always follow on, so the u's follow on. That's why I do this arrow thing. What's the differential of sine? Well, if you're not sure, cheat. No, I didn't actually say that, did I? Mary will shoot me for saying that. But, okay, so m curve, sine, m curve, steep positive, less steep positive to 0. Dun, 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 dun. They go that way. These are now negative to a maximum steep negative, so that coincides here. And then they're still steep, but they go back to 0. Who can tell me what this graph is? Positive. Who can tell me what this one is? If that's sine, this is?
Cosine.
Yeah. So the m, so y equals sine, theta, x, or whatever you. And then y dash is equal to cos. So there's a little way for you can do that, play with it. So this one here is going to be cos m, and the differential of this one is 2 out the front, 1 off, so we get 2x. So we've got dm dx. So our total is e to the u times cos m times 2x. Now you can see it happens fairly quickly, right? That all of a sudden you've got a lot. You've got to put your things back in. So we've got 2x e to the sine x squared cos x squared. And that's the result of your chain rule. Now, you know, because I'm a very erudite fellow, which is just complete rubbish, find me dy dx of e to the power bracket sine bracket x to the power 2, close the bracket, close the bracket. Let's see if that gives us the right look. And Mathematica has said, yes, I'm differentiating e to the sine x squared. Yep, so I've got 2x e to the sine x squared cos x squared. Tick. So we're at least as good as the technology that's available to us as students. Okay, so you've got your checker. Now the purpose of the checker isn't to cheat. The purpose of the checker is to help you do this. You must realise that this is a by hand subject. This is not going to help you pass the subject. The Mathematica thing, I inadvertently closed it, is not going to help you pass the subject if you rely solely on it. Okay, you will not be allowed to use it during assessments. It's solely there for your study and for your verification, because I don't want you to spend hours pulling your hair out wondering whether or not you've got a mistake at this early stage of your careers. Okay, so it's a checker. Now, how do we do this one as an expression? Goodness gracious. So d du, d dx, e to the sine x squared. Wow. So we do the same thing. We go and do u equals sine x squared. We recognise that as a chain rule, and so we let m equal x squared. Over here we recognise that we've got u, so if we need to we can go and do our chain rule. We're still going to have all of it, okay, but in the first instance we'll have a d to u. So our d to u will simply be e to the u. Okay, over here we're going to use Leibniz notation, du. Now we can't do that one that way, but we can do it as m. Okay, du the m, because u would be equal to sine of m. So du dx is going to be cos of x, cos of m, and finally we've got dm dx. So it's the same thing. You've got to be, this is very tricky. Look, once you get used to it, you'll find that you are on top and winning. Just link them together. and it comes out as the same thing. So that's e to the u. So e to the u is that one, cos m is that one, and 2x is that one. Okay, and then it's going to be the same thing. Okay, all right. So that's a good block of time that explores the chain rule and the kind of application you'll expect to encounter as you move forward through the calculus side of the subject. All right, the next thing I'm going to do is we're going to have a look at exact values tree, because I promised last week that that's what we would do. And from the second part, I think MWC, from the second part, exact values tree. Now this one here is the one that causes the most trouble, so we're going to have a good look at it. Now I'm just going to stop the video, and that's a good chunk of time.